Okay, I'm going to just talk through number 19 and 8.6. The original function was 1 plus x over 1 minus x squared. 1 minus x, that quantity squared. So what we can do is we can split this into two fractions, the 1 over this and then the x over this, that's this. And then realizing that x can be pulled out in front right here, I'm going to focus all my attention right now on this expression, which appears here and here. And I'm going to realize that that has something to do with the 1 over 1 minus u that I'm trying to get to, except that I've got the squared there. So what I've chosen to do to try and resolve the connection between the two is I'm going to take this expression, I'm going to integrate it. So I do that over here. I integrate this, make a u substitution, u is 1 minus x. Du is negative dx, and go through the integral. Rewrite this, bring the u squared up, use the power rule, and then from here I get 1 over u is the antiderivative, replace u with 1 minus x, and you've got this. So this looks exactly like 1 over 1 minus u. So in this case, u is going to be x. So I can always rewrite that as a power series. So therefore, if I take the, since the integral, the antiderivative of this, right, is equal to this, that means the derivative of this is equal to that. So the derivative of this is equal to that piece right there. So what I'll do now is I'll rewrite this function, f of x, and instead of writing this, I will write this, which is here, plus, so there's my plus, x, x, and then instead of writing this, again, I'm going to write this right here. And now the 1 over 1 minus x and the 1 over 1 minus x, turn those into the power series here and here. And then at this point, I'm going to differentiate both of these. So when I differentiate this power series, there's no cleaning up that has to happen. The n just comes down, n minus 1 there, and then notice the index goes from 0 to 1. And then I have plus x, and then the derivative here, again, the index changes to 1 and comes down n minus 1. All right, that's the heart of the problem. Now it's just kind of clean this thing up, get it into one sum. So what I'll do now is I'll take this expression, this x, I'm going to move it in here. When I move it in here, I put it right here. It comes together with this and it changes it to x to the n. This one, nothing changed. Then I'm going to try and make this one x to the n so that these two match. So I have to do that replacement. I need to make this an x to the n power, so I have to replace n with n plus 1. If I do that here, 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 then I will get this right here. And then the other one here I did not touch. So now these both have x to the n's, but the problem is that this one starts at 1 and this one starts at 0. So what I do now is I peel off the first term of this series. So I let n be 0. If I do that, I get 1 x to the 0, which is just going to be a 1. So when n is 0, this is 1. There's that. And then I go n is 1 and to infinity. So this is the rest of it. So that's just peeling that first piece off. Then I still have this second sum sitting here. And notice now both of these have x to the n. And both of these start at 1. So I can put these two sums together. So I can factor out an x to the n, and then I put the coefficient here, n plus 1. I add it, because there's addition here, to this n, and that's right there. When you put those two together, you get 2n plus 1, and your sum goes from n equals 1 to infinity. 2n plus 1 times x to the n, then I have a plus 1 out here. And that's it. That's your power series.